So now we are in lesson 7.2. It's exponents and logarithm. The first part for the exponents, those information you already know it from grade 9, but I will go over it quickly. When I say exponent, I have, for example, the form of a exponent m. We call a, it's the base, I'm sorry guys, and m we call it the exponent or the index or the power of a. When I say a exponent m, it means I'm multiplying a but by itself m times. You need to be careful, m should belongs to z plus and a is a real number. We have those rules, we know it already from grade 9. If I have a n times a m, if I'm multiplying the same base, I will add the exponent, it's an plus m. An over m, I'm dividing two numbers with the same base. To exponent the same base, I subtract the exponent. An exponent m, it's an times m. A minus n, it means 1 over an. Why? Because when I say a, it means a exponent 0. And now if I subtract the exponent, 0 minus n, it gives me minus n. Any number exponent 0 gives me 1. And if I have a exponent x over y, it means it's the radical y of x. So if I have this way like this here, this notation, it means a exponent x over y. So when I have, for example, radical 2, I can write it, for example, 2 exponent. Here it's 1 over 2. Let's do an example. If I have to simplify this expression, I have 15 times 4 exponent to n plus 1 divided by 25 times 2 exponent 4n. First, I'm going to write it as a fraction. If I look at it like this, I cannot simplify the 4 exponent to n plus 1 and 2 exponent 4n because it's different base. I can simplify the 15 and 25 easily because 15 it's 3 times 5 and I have 25, it's 5 times 5. I can simplify 5 over 5, it gives me 1. I don't have any problem with this, so I have 3 over 5 first. But what is the problem here? How can I simplify those? To be able to simplify it, I need to have the same base. 2, I cannot do anything to it. Can I simplify 2 more? Can I write it as an exponent? It's 2 exponent 1, it's the same, so it's 2 for n. What I can do to 4, I can write it to exponent 2. So 2 squared and then exponent to n plus 1. And now I continue the work. I still have the 3 over 5 times 2. Now I'm going to use the rule. I can even put it like this. 2 exponent to n plus 2, I will multiply, it's going to be 4n plus 2 over 2 exponent 4n. Now here I have the same base, so can I subtract the exponent? Yes, for sure. So it's going to be 3 over 5 times 2 exponent 4n plus 2 minus 4n. And then the answer going to be 3 over 5 times 2 exponent 2. So it is 3 times 4 over 5. So I'm going to write it 12 over 5. And this is my final answer. Another example, if I have to solve this equation, 2 exponent x minus 2 exponent 2 minus x is equal to 3. If I look at it like this, I cannot do anything here because it's a subtraction. It's not a multiplication to add the exponent. It's not a division to subtract the exponent. So I need to think about if I can see the 2 exponent x in this expression here. So if I look at this expression here, when I have 2 exponent 2 minus x, I can separate and write it 2 squared times 2 minus x, because here it was like this. When you add, you got the answer. What does it mean 2 exponent minus x? It means over. So I have now 2x over 1 minus 2 squared is 4 over 2x is equal to 3. And now I'm going to do the same denominator. When I do the same denominator, I'm going to multiply here by 2 exponent x. So 2 exponent x times 2 exponent x. Be careful, guys. It's not 2x squared. It's not 2x squared. It's 2x. All of it squared. It means the answer is going to be 2 exponent 2x. On purpose, I keep it like this so you'll not do the mistake. So here it's 2x. All of it squared. It means it's 2x minus 4 over 2x is equal to 3 times 2x over 2x. And now I will take all to one side, and I have a fraction is equal to 0 when my numerator is equal to 0. And now I have 2x squared minus 3 times 2x minus 4 is equal to 0. If you look at this expression on purpose, I left it 2x like this. I didn't write it to 2x to show you that it reminds me of a quadratic equation. So here it's something squared minus 3 times the same variable minus 4. So I can say let y be, for example, 2x. So if I replace y by 2x, I will have the equation y squared minus 3y minus 4 is equal to 0. Now I can see better that it's a quadratic equation. I can use the calculator to find the roots. I will have y is equal minus 1 or y is equal 4. And now we said let y be 2x. My objective is to find x. So 2x is equal minus 1. This is impossible. 2 exponent any number cannot give me a negative answer. And later on, when we're going to do the log, you're going to see why it's also not acceptable. Y is equal 4, so 2x is equal 4. I need to change to the same base. What is 4 is 2 squared. 2 exponent x equal to 2 squared. What does it mean? X is equal to 2. Now let's move to part 2 in this lesson. It's the logarithm. It's also very simple and very easy. Part A, it's definition and the domain of definition of the logarithm function. What does it mean, logarithm? It's a new notation. So if you see like this, if you see this notation, how do we read it? First, we read it log base b of a. This is the base. This one, it's the base. So log base b of a is equal to x. If I have this equation here, it means b exponent x is equal to a. So it means b exponent x is equal to a. So if I have a log expression, I can change it to an exponent. If I have an exponent expression, I can change it to a log notation. You need to be careful. A cannot be negative, b cannot be negative. So a should be positive and b should be positive. It's written here r plus, and b cannot be equal to 1 because 1 exponent, any number, gonna give me 1. What is so the domain of definition of log? All the time inside the log should be positive. So if I would give you, for example, log, I didn't write anything here, it means it's log base 10, and like you'll see it in the definition. So log of 3x plus 4, what is the domain of definition? 3x plus 4 should be positive, x should be bigger than minus 4 over 3. This log that you're going to see on the calculator, sure, when we're going to do more practice in the class, you will see that. And I cannot have a negative number here because the calculator will give me a math error. Now, let's do an example for what I did here. I can change an exponent to log. For example, if I have 3 exponent 4 is equal 81, how can I write this one as a log? So log, what is the base here? 3 of what? Of 81 gives me 4. I can change the log to an exponent. If I have log base 2 of 32 is equal to 5, it means 2 exponent 5 is equal to 32. And also I can sometimes, it's helped me to solve. If you have, for example, you need to solve for x. Log base x of 81 is equal to 2. How can I find what is the value of x? I just use the property. X squared is equal to 81. It means x squared is equal to 9 squared, so x is equal to 9. I can have different cases to solve for x. For example, here x is the answer. X is equal log 4 of 16. It means 4 exponent x is equal to 16. 4x is equal to 4 squared, so x is equal to 2. And sometimes the variable could be inside. So 5, 3 is equal to x, so x is equal 125. Guys, it's very easy. It's just about algebra. It's nothing more. Now we move to the properties of log. I should have the same base, if you notice here it's AA, to be able to use those properties. If here it's base A and here it's base B, I cannot use the same property. So log x plus log y is equal log x times y, so plus becomes times. I should have the same base. I will not read it anymore. Log x minus log y is equal log x over y. Log x exponent n is going to be n log x. Log a of 1 is 0. So log 1 of any base is 0 because any number exponent 0 gives me 1. Log a of a is 1. Why? Because also here when I say log base of a, I can write it this way. Log base a of a, it's equal log a over log a. Also we can write it this way. And what is log a over log a? It's equal to 1. Now log base a of x is equal, as I said now, it's log x over log a. and then you can change the base any base you want. When I have base 10, the notation is without anything. So this one that you see it on the calculator, you see on the calculator 2 log. You're going to see this one and you're going to see ln. You're going to see it later on. What does it mean, ln? So log base 10 of x, this notation, it's log x without any base. Minus log a of x, it's log a of 1 over x. Because here if you do the property, it's log 1 over log x, and you know that log 1 is 0, sorry, minus log x, so 0 minus log x, so it's minus log x. Log base a of b, it's 1 over, if you switch those, it's gonna be 1 over log b of a. And a log a of y, it's equal y because the exponent and the log are inverse functions, so it's gonna give me the same function. So if you have 2 log 2x, it's equal to x. Guys, all those properties, we will see it in the application. Let's do, for example, this expression. Let's simplify it. I have log 2 plus 2 log 3 minus log 6. If I want to simplify it, I cannot have here any constant. This one I should remove it first. So this one gonna become an exponent. And now I will lose the property of the addition that becomes a multiplication. It's log 2 times 9. 3 squared is 9. And then again, the subtraction, it's a division. So it's gonna be log 2 times 9 over 6. And the answer is log 3. Another example again, log base a of p minus 2 log a of q plus half log a. My problem is here first. So those cannot be here, so it's going to become exponents. And then I use the property minus it's over, and then the plus becomes a multiplication. So it's this times this one, I'm going to have the answer. Another example. For example, here you see that there is one that is log and the other one is not log. How are we going to work with it? We can change one to log base what? I wanted log base b of b. So, and now I can change the plus to a multiplication and I will get the final answer. Guys, it's very easy. Don't worry. We'll do more application in the class and you'll see how it's easy is it. Now, the last part in this lesson, it's Euler's number and exponential function. First, what does mean Euler's number? It's denoted by the letter E, and it's approximately 2.718. It's an infinite number. It's not accurate, so it's 2.7 normally we take it. You have it on the calculator also. Now, if it's given an exponential function ax, why I said an exponential? Because the only exponential function, it's ex. We will see it now in this video. So if I have an exponential function a exponent x, this function can have two possible graphs. If a is bigger than 1, if the base is bigger than 1, the exponential gonna be increasing. It's a growth function. X prime x is a horizontal asymptote and it's passing through 0, 1. And if a, the base, is between 0 and 1, in this case, it's going to be a decay function. It's also passing through 0, 1, and x prime x is going to be the horizontal asymptote. Let's do two examples and see how going to be the graph of a x. If I take, for example, g of x equal to x, this is an exponential function. You take any points, for example, x minus 1, it gives me half, x0, 1, x1, 2. And if you put the point and you join, you see that it is an increasing function. This is an exponential function. If I take h of x equals 0.5 exponent x, and also I take particular points and I plot it, you'll see that the function gonna be a decreasing function. So when a is between 0 and 1, it's a decreasing function. When a is bigger than 1, it's an increasing function. Now, for the function f of x equal to a of x, what is its inverse function? Its inverse function, it's log base a of x. But how are we going to prove it? Look how we can prove it. So y is equal ax. We know this from chapter 2, how do you find the inverse function. So now we switch y to x and x to y, and then now we solve for y. To be able to find the variable when it's in the exponent, we need to do log on both sides. So log x is equal log ay. And now the log, let me take the exponent down. So it's going to be log x is equal y log a. So what's going to be y? Log x over log a. It means it's log base a of x. So what is the inverse function of ax? It's log base a of x. Now, when a is e, now we say this is the exponential function. When I have here, I'm using e, the Euler's notation. And the inverse function of ex, it's log base e of x. But the notation of log base e, it's ln x. So this one, it means it's log base e. So on the calculator, you see log like this. This one is, we call it base 10. And when you see ln, this one, it's called base e. So this is base 10 and this is base e. Now let's move to the last example in this lesson. How are we going to graph the ln function? So for each of the following functions, state the domain, any asymptotes, and the coordinate of the x-intercept, and then we graph it. I'm going to just do this one because this one is a little bit more complicated than the other one. First of all, domain of definition. We know when I have an ln function, inside the domain should be positive. So 1 inside the ln should be positive. So 1 minus 2x should be positive. So x should be less than half. And this one gonna be the vertical asymptote because x cannot be equal to half. So the vertical asymptote is x equal to half. To find the x-intercept, we need to replace y by 0. By solving, by replacing y by 0, you will reach to absolute value equal to a negative, so it's impossible. It means there is no x-intercept. To find the y-intercept, we solve for x equal to 0, and the answer is ln 1 plus 3, so ln 1 is 0, so it's 3. So I have just a y-intercept, and I have a vertical asymptote. How do we graph it? To graph it, we start step by step. Step 1, I need to draw ln 1 minus 2x. I have my vertical asymptote, and I will take some points. For example, for x 0, y is 0. This is the point. For x minus 1, y is equal 1.1, so it's here. And my function is a decreasing function, so it's like this. So this is the graph of ln 1 minus 2x. I'm not done yet. I need now to do step 2, the absolute value. And also we know from chapter 2, when I say the absolute value of all the functions, it means all the y should be positive. So the negative y are not there. They don't exist. I should do the symmetry of the y, where y is negative, with respect to x prime x. So the function should be like this. So now if I want to graph the absolute value of 1 minus 2x, all what we need to do is to do the reflection of the y negative with respect to y prime, to x prime or x. And I should, guys, I need, what is the eraser? I need to erase this part. So now here I have, this is the graph of what? Of ln 1 minus, absolute value of ln 1 minus 2x. I didn't finish yet. I still have the plus 3. So what's going to happen to the graph? It's going to move 3 units up. So the last step, so plus 3, that's it. I not just need to move it 3 units up. So 1, 2, 3. And the final function should be like this and like this. I'm sorry. So this is the last function. This is the last figure of the function. That's it. This is the final result. This is absolute value of ln 1 minus 2x plus 3. That's it, guys. It's not hard at all. Don't worry. We're going to do more application and see you in the next video.